In this video, I want to have a little review of NMR and give another example. So again, remembering that NMR here stands for nuclear magnetic resonance. Why do we use NMR? Again, NMR really gives us some functional group and also structural analysis in some ways that we can't get from any other thing. So for instance, if we did some experiments such as elemental analysis, like you might do in general chemistry, you might do in quant chemistry, that gives us gross composition. So that might be, C6H10 or something along those lines. We could also do some chemical tests to determine various functional groups that are present that are along. IR gives us some identity of the types of functional groups that are present. For larger molecules, such as the ones we show here, the composition of functional group is not enough. These three ultimately all have approximately the same number of hydrogens and oxygens and carbons, and they're just all in different compositions. So, and I say approximately, but they have exactly the same number of those. What we find out is that all three of these, their IR spectra would look exactly the same, or very nearly the same. So this is the IR spectra of this compound. I couldn't find these two exactly, but I found something that was fairly similar. Again, the same number of carbons and all of that. But notice how these two look exactly the same. All right, so all four of these would have virtually identical IRs. All right, so that's really not quite enough information, so NMR helps to bridge that gap. So this is a sample spectrum, one that can be helpful. So again, let's just remember how we get this NMR spectrum. So you might remember that we can think about hydrogen nuclei, H1, that's what we think about here, hydrogen nuclei, and they all have spins that are all over the place. That is, they have a nuclear spin, and that just in nature, even though they're attached to this guy, again, they still have a nuclear spin, and their spins are just all over the place in terms of they're not aligned. We stick them in a magnetic field. We call that magnetic field HO, and about half of the nuclei line up with the strength of the field. We call those alpha. About half line up against it, and we call those beta. All right, so it's almost exactly 50% of each one of those, slight difference. Slightly more alpha just because they're lower in energy. The beta are a little bit higher in energy. So in a magnetic field, if we have these compounds, what we can do is hit them with enough radio waves so we can actually flip those that are in the alpha conformation or alpha spin into the beta. And because the beta is just a little bit higher in energy. And so we hit it with radio waves, and then again in the magnetic field HO, at least temporarily, all four, in this case we're just using four H1 nuclei, they would all line up with the magnet. And we could then detect what energy is needed to get these into that conformation. Also remembering that because these carbons and hydrogens are in different environments, they have different groups next to them, is that the radio frequency that's needed to sort of flip these into that orientation will differ. Also, let's remember that this term that we use for the energy that's flipping from this mixture of alpha and beta to all beta, remember this concept is referred to as resonance. All right, so we might say that we can bring the alpha nuclei into resonance with the beta, all right, so that they're all the same spin and that type of thing. All right, so this is really the background of NMR, why it works. As a result, remember we can get 4 bits of information. Number one, we can get the number of signals. All right, so notice here we have 3 signals. They have multiple peaks, and then this one and this one have multiple peaks. This is a single peak, but nonetheless, we can get the number of signals. We can figure out that there are 3 different signals. Number 2, we get integration. That is, that gives us the number of hydrogens under each peak. Again, this one we've written that on top, 3, 3, and 2. And again, those all correspond to A has 3, B has 2, and the C has 3. We can get chemical shift. Chemical shift is where these absorb here. Remember that C is a primary methyl in the end. It's typically between 0.8 and 1, but notice it's near an oxygen, electronegative atom, so it's pulled downfield just a little bit. A, which is really close to this carbon double bonded oxygen, and that oxygen is pulled further downfield, and again, but it's notice a single one, so it's a 2, even though it's a primary, it's down to 2. And then this B, it's immediately adjacent to an oxygen electronegative atom, and notice it's pulled way downfield. This one would typically absorb about 1.1 or so, and notice it's down to about 4. And that's all because of that oxygen. Remember, the oxygen is de-shielding the protons, de-shielding the protons by pulling away some of the electrons because it's electronegative. And as a result, it's more de-shielded, and de-shielded means more downfield. And then finally, the fourth thing we can get is the spin-spin splitting. And that, remember, is that non-chemically equivalent hydrogens split the signal of their neighbors, and that is hydrogens that are within 3 chemical or equivalent bonds, 1, 2, 3. So B and C end up splitting each other. A, as we can see, is unsplit. Now remember, this splitting is a result, or we can identify that as n plus 1 number of peaks. So let's just take this for C. All right, C, there are 3 of these hydrogens, and these are equivalent, and they don't split each other, but they are split by the 2 non-equivalent hydrogens here, the neighbors. So N is 2, 2 plus 1 is 3, and so the signal for 3 will be split into a triplet, and we see that 1, 2, 3. So we see that there. For B, these 2 hydrogens are chemical equivalent, but they are not equivalent to these 3. So N is 3, 3 plus 1 is 4. So notice the signal for B, its signal split into 4 peaks. So 1 signal, but 4 peaks. All right, that's really the power of NMR, that we get 4 different bits of information, and that can really help us to construct the molecule in terms of what it's how it's built. All right, so let's think about this. All right, let's think about how many types or chemically equivalent hydrogens that there are. So I might just pause and think about this one for a second. All right, so how are we doing? All right, so in this one, notice we almost have a bit of symmetry, and so we have these, and so in this case we just have 1 type of hydrogen. All right, so and all 6 of these are what we say chemically equivalent. B, we get 2 types. All 9 of these are chemically equivalent, but they are different than this CH3, which is here. All right, so this is 1 type. This is a second. Over here, somewhat similar, except we get 3. So again, how are those 3 different types? Again, all 9 of these are the same. They're chemically equivalent. So that's 1 type. This is a second type. The 2 hydrogens here, and this would be a third one. Remember that anytime we have an OH, remember this typically doesn't split others because of it's an exchange. And then finally on this last one, we also get 2 types. Again, why? We have these 3 and these 3, total of 6. These are all the same, and they are different than this one. All right, so again, 2 types that are there. And just that last one that we saw, again, bringing it together, we have the 2 types, the 3 red here, 3 red there, which is a total of 6, and then this 1 blue one. And so again, these 6 hydrogens, they absorb a little bit downfield, even though they're CH3, because of this iodine, this electronegative, it pulls them downfield, so it's absorbing here between 1.8 and 1.9. And again, there are 6 of those represented by this peak, so that's integration. So this is 1 signal, integration of 6, chemical shift down here because of electronegative atom. Notice it's split into a doublet. Why? It has 1 non-equivalent neighbor. All right, so it's a doublet. This 1 blue hydrogen absorbs pretty far downfield. So you can see here between 4.2 and 4.4. So why? This iodine's de-shielding it, so it comes into resonance further downfield. It has 6 non-equivalent neighbors, so it has 7 peaks that show up. Remember, the 2 that you can't see are really hard out there, little nubs. But if you count them up, there's a total of 7. And then I'll leave you with one final example, and this one involves benzene. And benzene, anytime there's a benzene ring with at least, it has 6 hydrogens, or even just a couple, benzene is characteristic that it always absorbs between about 6.5 and 9, and it always a fairly ugly peak because these are all splitting one another and they show up. And so notice this is just one big smear as opposed to individual peaks that show up here. Alright, so this is one. So again, we'll pull this away. This is ethylbenzene. Alright, so we have CH3, CH2 in this group. Pull this back away, and then down at the bottom, which I'm not able to show you right now with a highlighter because the little palette covers it up, but notice that the CH3 on the end is A, the CH2 is B, and then all of the benzene rings are C. So notice it's showing the chemical shift to where these show up. Alright, so let's bring in, there's our table. Bring in our table. So a couple of things. Notice that we have a CH3 and a CH2. Those are typically 0.1 and about 1.2. Notice they're downfield. Alright, so the CH3, which is here, is downfield about 1.2 or so, and this one's about 2.5, 2.6. So why is that? Well, again, this benzene ring is helping to pull them downfield because it's basically withdrawing some of those electrons. So that's why they're not quite in the exact position. So we see that, and then also notice that the benzylic, and then we see that here, the benzylic, which is CH2 next to, is about 2.2 to 2.5, and we see that that's the case here. It might be just a little bit further downfield, but it shows up about 2.25. So the benzylic, the AR, which stands for aromatic, AR is aromatic, CH2R, again, shows up at about 2.2 to 2.5. And then also if we come down here to aromatic, see this guy, 6.0 to 9.5, and you can see that those are these guys here. Alright, so again we have 3 signals because we have A, B, and all of these are what we call C. Even though they may not be exactly all equivalent, they all show up in a general spot, and aromatics really have this ugly looking peak. So we have 3 signals. We get this one doesn't show us the integration. Sometimes it's written above, and this one we may just have to sort of look at it. But we can get integration from a computer or from a program if we have that. We have already looked at the chemical shifts for these, and we can also see the spin-spin splitting. Notice the benzene ring, no splitting here. For the CH3, which we've called A, it's got 2 non-equivalent neighbors, and so it should be split into 3 peaks, and we see that here. It's a little bit tough to see they're together, but we have an outside peak, a tall inside one, and another outside peak. The CH2, which we've labeled B here, they should be split 4 times because they have 3 non-equivalent neighbors. 3 plus 1 is 4, and indeed we see that we have 2 outer smaller peaks and 2 inner larger peaks, and that gets us for this. But this is a sort of a classic example of what happens when you have benzene, that you have a big smear of peaks all on top of one another, and they look pretty ugly, and it's always between about 6.5 and 9. Alright, so anytime you see something between 6.5 and 9, and it sort of just has a bunch of stuff over top of it, that should be like a big red stop sign there. You should just stop and you say, alright, that's got to be benzene, and that should give you some indication. It's not that nothing else can absorb in this region, it's just that the most typical is benzene, and that also it sort of has this ugly look to it. Alright, so again, another example of an NMR spectra. Alright, so use this bit of information as you're working on your activity 13 of NMR, and also as you're doing your lab sheets, the lab NMR sheets, and as you're really just trying to do your homework as well. Alright, so again, using the information that we've covered and in the other videos and this one to help you solve NMR spectra.